Let us now present a very simple extension of histogram equalization, which is called histogram matching. So let's just illustrate the problem. We saw before histogram equalization where we take any histogram, any pixel distribution, and we match it to something which is as uniform as possible. But imagine that we have this pixel distribution, which is the one we have seen before, and somebody comes and tells us, this is your target. I don't want to do an equalization. I want you to finish with an histogram which is as close as possible to this one. So the idea is, as before, we're going to have to find a map, which is written here. This is the map that we have been doing before. A map such that from here, from this distribution, we can go to as close as possible to this one. In this case, in the way that I'm going to describe in a second, what we are going to obtain is this, which is very similar, not exactly, but very, very similar. We already saw in the previous video that we cannot always get exactly the specified histogram. In the previous video was equalized, but we can get very close to it. And this is what we see here. So how do we do that? You already have all the tools to do that. Let me illustrate how. We start from the distribution of the current image. Whatever that distribution is, it's the image that is given to you. You know how to map that to a uniform distribution, okay? Now, you are giving a desired distribution. You know how to map this desired distribution, the target distribution, also to a uniform distribution. Therefore, if you know how to go from here to here and from here to here, if you invert this, you know how to go all the path that is the desired path. So you're going to map a pixel value from here to here. Then you're going to ask, okay, where is this pixel coming from, this pixel value coming from when I want to go here? And you just invert that. So you basically have one map, another map, and you just invert that second map. So let's say that pixel value number, a pixel with a gray value 7 goes to 10 here. Then you ask, okay, who from here, what pixel value went to 10? And somebody, this map tells you 15. So you end up going from 7 to 10, and inverse of 10 is 15. So you went from 7 to 15. And that's how you basically get an histogram matching. Just by doing histogram equalization, now you know how to match any two desired distributions. There's one caveat. As we saw in the previous video, the maps don't have to be one-to-one. So maybe there is more than one pixel value here that ends up at the same pixel value there. So when you go from 7, let's say, to 10, maybe there is 15 from here goes to 10, and maybe also 20 goes to 10. So am I going to map 7 to 15, or I'm going to map 7 to 20. You're going to have to make a decision. The most common decision is to pick the one that is closest to the original, so you do the less deformation of the pixel values of the image. But you can make other decisions as long as those decisions are consistent and as long as those decisions guarantee that you end up with an increasing function. Remember that we don't want to flip pixel values. So once again, you do two histogram equalizations, you invert one of them, and then you basically obtain histogram matching. So let's see how that works. This is a particular example. We have a very dark image here, and we see that in the histogram, mostly dark values are used. So it's hard for us to see what's going on here because it's very, very dark. If we do histogram equalization, we get a too bright image, as we see here. This is actually the mapping, the TR mapping that we always are looking for. And this is going to be the new histogram. And we see both from the histogram and from the actual image that is way too bright. So we haven't achieved what we really wanted, which is a nicer looking image that we can actually observe the different regions of that image. If instead of that, we do histogram matching, so somebody comes and tells us, I know that this is the distribution that is going to be great for my image. Then what we do is, again, we go from the original distribution to equalization. We go from this distribution, the new distribution here, we go to equalization, which is going to be this map. We invert that map, which is going to be this. And then we go in 2 steps from the original histogram to the equalized one, from the equalized one through the inverse map to the new pixel value. And we get this distribution, which gives us this image, which looks much nicer than this one. And it also helps us to look at some of its details. So we basically got histogram matching by doing twice histogram equalization. Once direct, and the other we just invert it. And again, if we have ambiguities, we just make a decision by using, for example, the pixel value closest to the one that we started in the original image. So you got 2 for the price of 1. If you know how to do histogram equalization, you know how to do histogram matching. Of course, there is a big art in designing your target histogram, and that's very application dependent. Let's just mention one last thing about histogram equalization or histogram matching. So far, we consider the whole image, and we say, let's just look at the whole image, let's look at the distribution, and let's match those pixel distributions to a new distribution, either an equalization or a specified distribution. You can do the same operations locally. So for example, if we take this and we do global histogram equalization, we are going to get this. Sometimes it looks a bit better, but there is a compromise. I only have 256 pixel values to distribute for my whole image. So I might not be able to do a very strong contrast at the same time here and here. So the way to solve this is to basically consider regions and say, let's just do histogram equalization, for example, of this region, and let's do histogram equalization of this region. They can actually be overlapping, and we are going to treat each region independently. And maybe by doing that, I can basically improve the contrast in every region in the image when there is a large variability, like in this particular image. This is a result of that. And I want you, for example, to concentrate on this region. How it's very hard to see the details here. They don't look much better here, but they do look much better here. Now, in this region, there's not a lot of details. The global did manage to do a good job, but not in this region. Global histogram equalization or global histogram matching is a compromise between everything that we see in the image. We can try to overcome, at least partially, that compromise by doing this local operation. And now we see that you can get details here. We can also get details here. So in the different regions of the image, they have very different pixel values, and we can still do basically a histogram stretching and get much better contrast in the different regions. By this, we basically conclude our unit, our portion on histogram equalization and histogram matching. A very simple operation and very useful. See you in the next video. Thank you.